Thanks to the organizers for having me. And I want to send my well wishes as well to everybody there who's been affected by the fires. So what do I want to talk about today? Well, I want to talk about trying to understand the magnetic fields of planets. So we've heard a bit about this or touched on this maybe a bit already, and how we can use these objects called ultra-cool dwarfs, which you may be familiar with, to try and further our understanding. So why do we care about magnetic fields in exoplanetary systems? There's a lot of reasons, and magnetic fields really underpin a lot of the key processes that we've already touched on so far in the conference, from the formation of these planets in their protoplanetary disks to understanding what's going on inside these planets. We'll hear a bit more about this from Elise in this session about perhaps detecting planets due to interactions with magnetic fields. And then something which, of course, most people in the room actually care about is atmospheres and habitability and how do magnetic fields affect these, right? So we so d diving into one of these a bit more now. In terms of the atmospheres, you can see here on the left-hand side some simulated uh, images of what the effect of atmospheric escape is like for a planet depending on its magnetic field characteristics. And you can see as you go from a planet that's unmagnetized all the way down to having a very strong magnetic field comparable to Jupiter, that the amount of neutral hydrogen escaping from this theoretical planet actually increases. So the strength of the magnetic field is important for these interactions. And another thing that's also important is the geometry and orientation of the magnetic field of the planet relative to its host star. And so you can see here on the right-hand side what happens when you tilt the magnetic field towards or away from the star and how this affects the escape of oxygen plus in this example. So we want to know the magnetic fields of planets, right? I think this is pretty obvious. And okay, the next question is then how do we measure them? So one direct way to measure magnetic fields is through the Zeeman effect, right? This is the splitting of spectral lines in the presence of a magnetic field. And in extrasolar systems, this has been very successful for measuring the magnetic fields of stars themselves. So here's just an example of the magnetic field strengths of stars or M-dwarf stars as a function of this property called Rossby number. You can just think of this as rotation period for simplicity. And you can see that we can develop these trends in rotation period and so on and so forth, and kind of probing activity and things like that as well. And so this measuring the Zeeman effect has been utilized extensively to the point where we can actually map the magnetic field of stars. And so you may be seeing magnetic field maps of the surface of the Earth, for instance. So we can actually do this for stars outside our solar system as well, just by observing the Zeeman effect and watching the star rotate. But the question is then, okay, does this work for exoplanets? Short answer is no. They're way too faint. Have they're lacking the magnetically sensitive lines to even do this. And they're very difficult. Even if we could detect them, trying to model the molecular forest of lines of these objects in terms of Zeeman splitting is just sounds like a nightmare. So we need something else. And what we have converged on over the last 30 years or so is to actually use radio emission. So I forgot to say at the start that I'm a well, I'm not a radio astronomer, I'm a radio modeler. So that is where this comes into this. And so in the solar system, the magnetic fields of the planets are signaled by radio emission. And for simplicity, I've split this up into two separate processes, which are fairly well understood at this point, thanks to many in situ observations with Juno, for instance. And the first one of which is you can see on the left here, and it's due to these interactions between the volcanic moon Io orbiting around Jupiter And so Io spits out material and builds up this sort of plasma ring around Jupiter, and then the magnetic field can interact with this. And so this interaction accelerates electrons along the magnetic field lines. And so you can see just an illustrative example of this being lit up, or Io is effectively lighting up the magnetic field of Jupiter. And then on the right-hand side, we can see a scenario where we don't actually need an outgassing moon, but we can just use the plasma flowing out from the sun, and some of that energy effectively squishes the magnetic field of the Earth on the night side, and this causes magnetic reconnection to happen. So we can have an alternative source of electron acceleration. And so both of these processes produce very bright radio emissions. So ideally, we want to try and detect this kind of emission from other exoplanetary systems. And this will allow us to then characterize their magnetic fields and understand their atmospheric processes, for instance, a bit better. Zooming in on this kind of electron acceleration mechanism a little bit more. Well, for simplicity, we can refer to this as auroral radio emission. And so we have a magnetic field line, and then we have the planet on the left-hand side, and something accelerates the electrons. We don't really care what it is; it doesn't really matter for right now. Um, and so this produces radio emission. Okay, um, this emission is nice in that it is encoded with the characteristics of the underlying magnetic field. So the frequency that it occurs at it scales directly with the magnetic field strength. So if you look at a certain frequency and you detect this kind of emission, you know that you're looking at emission from a magnetic field of a certain strength. And another nice property of this type of emission is that it's beamed outwards in a cone shape. And I was presenting this recently, and somebody told me this reminded them of a dog with a cone on his head. So I've decided to put that in there and leave that there. So you can think of that. And so the point here is that the visibility of the emission very much depends on the orientation of the magnetic field relative to you, right? So it encodes this geometric information. And so in theory, this emission gives us everything we need to fully characterize the magnetic field. But I hate to be the bearer of bad news, but there have been no conclusive detections of radio emission from exoplanets, despite many, many efforts. But there are these nice objects in the middle, which I've become very focused on in recent times, called ultra-cool dwarfs. So these are effectively massive isolated Jupiter analogs, right? And the nice thing about these is that we do actually detect these kind of auroral radio signatures from these objects. And so then the angle here is that, okay, these objects share many similarities to Jupiter. And so by studying their radio emission, we can characterize their magnetic fields. And so moving on to a specific example of what we can do with this kind of observations. So this is a T8 dwarf. It's the coldest brown dwarf ever discovered in the radio, I should say. And you can see its light curve underneath here, which has some interesting structure in it. A fun fact: this brown dwarf is roughly the same temperature as a pizza oven. Um, and so we detected a lot of interesting structure from this object, and we were thinking, okay, well, is because there's so much information in this nice light curve, can we actually properly characterize or invert the magnetic field geometry of this object? And so we took an approach that looks something like this, where we let different magnetic field lines in a global magnetic field emit radio emission in this cone shape. And then we tried to invert the geometry. And so after lots of head scratching and battling with nested sampling algorithms, you can actually get this to work if you have good enough data. And so this is the fit that we obtained for this T8 dwarf. And so what does this actually look like? So what we inferred was that we're looking at this object effectively pull on, and it has a very oblique magnetic field. So this means that the magnetic axis of this brown dwarf is effectively perpendicular, and so it precesses around kind of like a pulsar, if you're familiar with that. Um, and it also has a magnetic field strength of at least 600 Gauss. So this is like 60 times greater than Jupiter's magnetic field. So, we can do these kind of characterizations for a wide range of ultra-cool dwarfs with this framework that we built up. And we can maybe say something about the internal composition of these objects. For instance, Uranus and Neptune have very oblique magnetic fields as well. If anybody is familiar with this topic, I'd love to chat more about this. So please get in touch if you have any expertise, because I do not. And so my time is coming to an end. So I'll leave it there, and I'll leave you with these take-home messages in case anyone is just waking up from a nap. So we can characterize magnetic fields very nicely using radio observations, and ultra-cool dwarfs present this nice opportunity to bridge our understanding of magnetic fields from stars to planets in this period where we can't actually detect exoplanets directly. And something I didn't have much time to talk about is just the fact that, okay, we detect radio emission from ultra-cool dwarfs, but we actually have no idea what the source of plasma is around these objects. And so one enticing possibility is that there are, like Jupiter, outgassing moons or planets even around these objects. This is a big challenge in the field to still figure out, and it requires a lot of complex numerical modeling. And so that's a big mountain that somebody will have to climb. So that's me done. Thanks for your time.
I don't know if you can hear it, but people applauded.
Thank you.
Yeah, are you a grad student? Yes. Awesome.
Hi, Rob from Across the Seas. Good talk. I'm curious, for someone who's not familiar, is that very strong magnetic field for the ultra-cool dwarf that you identified, is that in the regime that we would expect? And if so, or if not, what would cause such a strong magnetic field?
Thanks for your question. So it's actually a lot stronger than what we expect. This is not a new finding. So um, over 15 years ago, um, a scaling relation was developed effectively to estimate the magnetic field strengths of these kinds of objects just based on their internal heat flux. Okay, so their magnetic fields are generated by a dynamo, and so we can, in theory, estimate how strong their magnetic fields are. But it was discovered about 6 or 7 years ago that these types of objects they start to diverge from this scaling law, and they're much stronger than what was expected. So I think we definitely need to refine these dynamo simulations a bit better in this kind of regime. One thing that these simulations can't tell you is about the magnetic field geometry, though. So that is another thing that needs to be addressed in future.
So Rob, thank you.